Greetings, everyone.
Hello.
Let me share my screen.
afternoon.
So you can all see my screen now?
We can indeed.
All right. Nope, but not up there. Oh, thank you. Now, there we go. Okay. So today is our last official class day, but we still have a final exam on Wednesday, May 5th from 3:30 to 5:30. So going to talk about a few things with that as we start class today, and then we're going to finish up functional programming languages today, talking about evaluation order with lazy versus eager evaluation, generator functions, which are the last problem on your homework assignment. So the exam, I have published a review guide for it. So it covers everything from the layout lectures in GUI. So basically, it starts here with layout algorithms for widgets. That is the first potential topic that you need to deal with on the final exam. And I have decided not to have a complete scheme programming question. Instead, the scheme.
Thank you.
You're welcome. There's a slight caveat to that. So if you look at the sample exams, so you will be confronted with this kind of question. Suppose you want to write a scheme function to reverse the elements of a list. Which of the following functions would correctly perform this task? So basically, I'm still giving you a problem that I would like you to write, but I am then proposing a number of possible solutions, and you need to tell me which ones you think work. Okay, so you don't have to generate it from scratch, but you do have to be able to look at the code and figure out if it implements the function that I've asked for. Another thing I might do is give you a function that has an error in it, like say lacking a base case, and ask you to fix the function. So you wouldn't have to write the full function from scratch, but you might have to fix it in some way. So those are things. So as an example that I will point out what is a wrong answer here, but it's not wrong by much. So right here, this answer is for reversing a list is kind of close, which is it is consing the cdr of the list with the first element and putting the first element seemingly at the back. Okay, so this looks like it could be the right answer, but the problem is that statement creates what is called an ill-formed list, because a list has to end with a null list. It can't end with an actual element. And this is creating a list that ends with an actual element. So it's called an ill-formed list. So that would be an example of something where I might tell you you need to fix that problem. And turns out that this statement right here fixes this problem. So the actual thing you had to do was create a, first of all, you had to convert this into a list. And then you had to use append, not cons. And you couldn't just, coulder of L didn't actually reverse anything. Okay, you had to actually call reverse list on the rest of it. So probably not something quite that difficult, but I'm just trying to show you how I might give you something that's close to right, but not quite right, and tell you to fix it. Okay. So I have not actually written the test yet, but for sure, I'm planning on a question of this type. I'm not so sure about asking you to fix anything. And I will probably again do a sample quiz just so that you all make sure that everything seems to be working. If you want, you can take it in class. And if you do, you won't have to use the lockdown browser to take the exam. If you're not going to be here and taking it remotely, then you're going to have to use the lockdown browser to take the exam. Will basically be the same setup as we had last time with you, logging into a Zoom session on an iPhone and using the web cameras so that I can monitor everything. And if you're going to show up in class, please let me know. So far, only one person has actually said that they're going to show up in person for the final. Just gives me a rough idea of how many people I'll be dealing with in class. So, questions about the final?
Is there gonna be partial credit? Like if most of the questions are multiple choice or fill in the blank, is there any opportunity to get partial credit or no?
Yes. So all semester you've been bedeviled by the fact that Canvas taketh and then giveth, or giveth and then taketh away. I will override that for the final. So in the final, if it's a multiple answer question, I will say, you know, 2 of the answers are correct. And I will then go through and manually ensure that if you get one of the 2, you get half credit. So yes, I will basically, for this final, I will override, I will go through and manually grade stuff. Other questions?
Okay, and
Oh, go ahead.
also, will we be allowed to use like handwritten notes just like the midterm?
Yes, so it's open note, open book. You'll be able to use the Xi book. You'll be able to use my notes. You'll be able to use your handwritten notes. I'll make
Okay.
the same plea that I made before the midterm, which is I think the very best thing you can do is create, in this case, we had, I would say 4, maybe 1 or 2 page crib sheets, one for GUIs, one for Python, one for functional programming, one for concurrency, that basically has almost anything you think you'll need, because it's not fast to access things through the lockdown browser. It's slow. And I don't design the exam with the assumption that you're going to be leafing through your notes. I basically do it with the assumption you pretty much have everything at your fingertips, and that it's pretty much instantly available, the information you need. So again, I think the best way to prepare is to have 4 crib sheets, one for each of the 4 major topics in the second half of the course. And basically that way you have a quick reference guide, and printed or handwritten, whichever you prefer. Other questions? Okay. So then just with the homework, whoops. That is due basically Thursday morning, so you have tomorrow to work on it. And as I say, no late submissions because we need the TAs to be able to start grading it so that I can get everything in to the registrar at the times that they want. Office hours. So I have an appointment at 3:15, so I'm only going to have short office hours today from 2:35 to 2:50. However, just like last night, I am planning to have some impromptu office hours tonight. So I don't yet know my schedule, but sometime between 8:30 and 9:30, I will log in tonight on Zoom on the office hours link, and I will hold office hours for about an hour. So feel free to ask me questions then. And then tomorrow from 11 to 12 in the morning, I'll hold office hours because I know a lot of you are coming down to the wire and may want some help. So hopefully can deliver that. Okay, so today we are wrapping up our discussion of functional languages, and we're going to talk about evaluation order. We're going to talk about some of the problems that confront the developers of functional languages and their implementation. Basically, how the lack of side effects can create problems for people who write Lisp interpreters and compilers. And we have time, I still want to go through that simulation of the deterministic finite automata. But we need to make sure we get through the other stuff first. The big thing I know is the last problem where you're asked to do Fibonacci numbers. And at the end of class on Thursday, we went through an example with the natural numbers, which wasn't quite, it doesn't exactly mimic what you need to do. It mimics it in that the problem I gave you is a two-part problem. One is define a stream of Fibonacci numbers. And for that, you can pretty much use this natural number template as a template for creating your stream. The second part, though, is different than the example here, because the example here with the natural numbers is only showing you essentially how to force out like the first value or the second value. And what I'm asking you to do in the homework assignment is print out some number n of those Fibonacci numbers. So here is my, first of all, a kind of guide to it. Then I'll show you more specifically what I have in mind. So the first part, you need to create a so-called list where what you have is a cons pair, and the first item is actually already available. It's the next item in the stream, and the coulter is a delayed call to your generator function. It is the part that is like a promise to be generated in the future. And the delayed call should contain any parameters that you need to create the subsequent item. So where you stop is kind of like the delay call is kind of like the yield call in Python. So it's where the computation temporarily stops. And then force causes the computation to resume. So once you have your stream function, you have to be able to write something that will process it and force it to generate items for you. So Again, the idea is, it's as though you have a virtual list, but only the first item of the list has been generated. The rest of the list is virtual. So if you want to think of it that way, it's a good way to think of it. So when you write your function that's going to print out the first n Fibonacci numbers, then you can assume that the first item of the list is physically available in the car of the list, but that the rest of the list, the cdr, is virtual. And in order to generate the next item or the remaining items on that virtual list, you're going to have to make a recursive call to your function. And you're going to pass it the cdr you're going to pass it the cdr, which is the virtual list, and then you're going to prefix it with the force function to force evaluation. So the tail function performs this task here. It basically forces the evaluation of the cdr of a stream. So basically, what is going on is you have your stream object, and it's really a cons pair. And the first one is a physical value. It's already been realized. And then the second thing is a virtual list. So your function that's generating the Fibonacci numbers essentially is going to first display the car of your stream. And then it needs to recursively call itself on this virtual list. So then after it's done the display, it effectively has to do a force. It basically has to, so if you have this function, call it printer, and essentially it is taking a stream object and a number n to print. It's the number of objects you want to print in the stream. Then the thing is, if it's, you have your base case, so I want to erase this. So your base case, I'm going to write it out more imperatively. So if n is equal to 0, we're finished. So you're counting down essentially. Otherwise, you want to display the car of it and essentially call printer, and you want to force the cdr of the stream with n minus 1. So basically, you're doing a recursive call where you always have the stream always has the first element has been physically realized. Okay, again, when you get the stream, it's a value, and then it's effectively a virtual list. The virtual list is really something that has been delayed, and you have to force it. Okay, so if n is 0, we're finished, else we display that first item which is available, and then recursively call ourselves by forcing the evaluation of the cdr of the stream. So that forces the evaluation of this virtual list. The evaluation always gives us the next item plus, again, a virtual list. So that's a pseudocode for what you're going to have to do on the final problem of the homework assignment.
I have a brief question.
Yes, go ahead.
So you're abstracting the stream by just saying stream. I don't understand how the number we pass to Fibonacci needs to change as we do this. Because if I do anything higher than like 2, I say it's not a procedure, because we're replacing this car stream with force CDR stream, right?
Right. So, but okay, so you should be able to write, let's go back to here. So actually, let's go to the homework assignment. Okay, so you're going to have to, basically, you're changing this because right now, this Fibonacci function is just producing the nth Fibonacci number. And what you want it to do instead is you need to modify it so that it's creating like a virtual list for the Fibonacci numbers. But you still should be able to make a call to something like fibhelper and update the parameters like this. So F2 plus F1 plus F2, and you're just going to be adding a delay function. So I may have to look at your code in order to see what it is that is causing your problem. So
frankly, I've spent hours on this, and I don't know if the time I've spent on it is worth the 10 points that I'll get for it, especially since I've already submitted early. So
okay, just stick around after class. Let me take a quick look at it after class, okay?
All right, man. I don't want to bother you.
Well,
right, it's not a matter of points now, it's a
without,
matter of pride. I can't let it go.
Right, I know what you're saying. And it's hard for me without seeing your code to know exactly what it is that's bedeviling you. So the let's see. But so I guess what I'm trying to say is here you can see that the way it's generating the next natural number is it is calling plus n plus 1. So that gives me the next natural number, but I'm putting a delay, whoops. I'm putting a delay right there so it doesn't get immediately evaluated. It gets evaluated the next time we start up evaluation. So the idea with fib is that in this cons pair, n would be your next Fibonacci number, and then this fib call would basically be setting up to generate the next Fibonacci number. But I know that's somewhat general, but I don't want to, I guess, give away completely the answer. So that's why I'm saying after class, I'm willing to take looks at code and maybe give, based on what I see, I can give more specific clues.
Sure, and if people have other questions, I don't mind taking a back seat, because like I say, it's not going to hurt me to miss out on the 10 points. But
Gotcha. Okay. Other questions? Okay. So there is, sorry, in functional programming, and actually in any imperative language as well, there's a notion of the evaluation order of arguments to functions and to special forms like if then else, switch statements, conditional ands versus regular ands, ors. So the question is always going to be, before you execute something like an if then else or a Boolean and or a function? Do you evaluate all the arguments, or do you just evaluate ones that you need? And in imperative languages, this is what you're used to, is evaluating all arguments before invoking a function, and that's called applicative order. It might also be called eager evaluation. And there is a second kind called normal order, which is just-in-time evaluation. You don't evaluate an argument until you need it, and that's called lazy evaluation. Okay, and it's sometimes faster if you end up not needing that argument. So for example, the conditional and, you don't actually want to do this division if y is 0, because if you did it, you would get a divide by 0. So, and not only that, but even if, well, in this case, you're going to have to do the division if it's not 0. But in some cases, if the first branch of the and is false, you save time by not evaluating the second branch. Okay. So in general, though, normal order is slower than applicative order. And the reason is that it may have to evaluate the argument multiple times. So here's an example where I'm just adding x with itself. And I'm calling double with times 3, 4. So the argument is times 3, 4, or 12. And the result should be 24. So with applicative order, that function is immediately evaluated and it gives 12. And so when I do the addition, it's 12 and 12 and I get 24. With normal order, it's more like a macro substitution. So wherever you see x in the function, it's replaced with the expression that computes x. So you end up with plus times 3, 4 times 3, 4, and you perform the evaluation twice, which slows down the program. So normal order looks more like macro substitution, where whatever is the expression for the argument is literally substituted for the expression in the function. And you save time if that argument never has to be evaluated. But if it has to be evaluated more than once, you lose time. And as we all know, generally arguments are evaluated one time or more, so normally normal order is slower. Okay, so in Scheme, they use the normal applicative order for functions. I checked this, so the version of Scheme we had a few years ago did evaluate the arguments right to left, but the Gambit interpreter actually evaluates the function arguments left to right, which is what you would expect. Now, there are a few special forms that use normal order. So they are if, cond, Boolean, so those are exceptions. So with an if statement, you begin by evaluating the condition, and then you evaluate either the true expression or the false expression, but you don't evaluate both. With the cond, you start with the first cond expression and evaluate it, and you continue until you find a cond that evaluates to true. Any remaining cond statements are ignored. And then with Boolean and or, with the and, so the and, if first condition of and is false, second condition is not evaluated. And with the or, if the first condition of or is true, sorry. Actually, I think or is, doesn't matter. Or you would keep about, if it's false, yeah, with, no, it's not true. So yeah, with or, if the first condition is of or is true, second condition is not evaluated because the or is guaranteed to be true. So those are three scheme special forms where it uses normal order evaluation to do it. So languages, you'll sometimes hear a language called strict. A strict language requires all arguments to be well defined so that applicative order can always be used. And essentially, almost no modern language is completely strict. So for example, C, C++, and Java all use conditional and conditional or. So a non-strict language does not require all arguments to be well defined and will do some normal order evaluation. So they say C is strict except for the Boolean expressions. Okay, then the last thing with evaluation order, this is actually not so much evaluation as it's an optimization technique for functional languages. And someone asked about it actually a week and a half ago. So because of the lack of side effects in functional languages, you can cache the results of evaluating a function. Basically, in a hash table, you can store the name of the function and the values of its arguments. And before you evaluate a function, you can check to see whether it's in the hash table. And if it is, then you just return the value from the hash table rather than evaluating the function. And we saw that for Fibonacci numbers, that was a huge win because if you remember, if you do a naive implementation of Fibonacci numbers, like say fib of 10, then that will do fib of 9 and fib of 8. That does fib of 8 and fib of 7. This does fib of 7 and fib of 6. Fib of 7 and fib of 6. And you can see already this evaluation is going to give the same result as that evaluation. There's no reason, if I've already done this evaluation right here, I don't have to do it a second time there. So memoization is a process where I remember the results of previous function calls, and if the parameters exactly match the parameters to a previous function call, instead of doing the function call again, I simply return its value. And using that, you get a performance of normal order evaluation that's within a constant factor of applicative order evaluation. So coming back to this example right here, memoization would actually, the first time it evaluated this argument times 3, 4, it would save it rather than doing an actual macro substitution. So it would memorize the result of times 3, 4, and the second time I needed it, it would simply return 12. It would know that it had already, it would look it up and see, oh, it's already evaluated to 12. So it will still be a bit slower using memoization because you have to do a lookup, but it at least brings it to within a constant factor. So Fibonacci numbers are no longer exponential, but would be order n. And spreadsheets use this memoization technique extensively. So if you have a set of equations, let's say you have these 5 equations. So B9 equals 5 and C9 equals 10 are equations. Then it saves or caches the result of each of these evaluations. That's what you see in each cell of your spreadsheet. And if you change a value like, say, B9, it's only going to reevaluate the equation for B10 and the equation for A10. It's not going to reevaluate the equation for C10 because that equation is not affected by a change to B9. So the spreadsheets automatically use a memoization technique to speed up their execution. Now, it depends, memoization depends critically on the absence of side effects. If you allow side effects, it will ruin memoization. So for example, I set x to 5 and y to 10, and I evaluate the expression times x and y, a good Lisp interpreter will cache that result. And the next time you multiply x and y, it may assume that the result is 50 because it's assuming x hasn't changed. But if you imperatively, I don't let you use this command, but set with a exclamation mark will change the value of x, and that messes up memoization because now when you try to multiply x by y, the result should be 10, it should not be 50. So memoization relies very strongly on this notion of no lack of side effects. Okay. Okay, so we do have some time. So I promised you a more significant problem with functional programming, because what you all have been doing, while I know it's difficult, they're not doing a whole lot of super complicated processing. So what I want to show you is an example where you're going to simulate a finite state machine. Any finite state machine. So you want to write an interpreter that will take any set of states and an input, and it will simulate a deterministic finite automata. So as an example, the one we will be dealing with is a 4-state automata that returns true for any string that has an equal number of zeros and actually an even number of zeros and an even number of ones. So if you have second. So for example, 1 1 1 0 1 0, that's a string that we're going to accept because it has an even number of ones and zeros. We would not accept this string because while it has an equal number of ones and zeros, it's odd. Okay, we would also accept the string, this string, because it has an even number of ones and an even number of zeros. So what we're going to provide as, and you can see what the finite state automata is doing is going to different states. So the Q0 state is the one where it's even zeros and even ones. Q1 is a state with odd ones and even zeros. Q2 is a state where both the ones and zeros are odds. And Q3 is where we have an even number of ones and an odd number of zeros, seen thus far. So each state is saying where we are given where we are in the string. So for example, if we have the string 101101, starting at 1, we would go to Q1. Then the 0 would take us to Q3. So sorry, the way it has it, Q3 is the one with an odd number of ones and odd zeros, and Q2 is even. So when we see this 0, we go to Q3. So we're now with an odd number of ones and an odd number of zeros. When we see this one, we come to Q2 because we now have seen an even number of ones and an odd number of zeros. When we see the next one right here, we return to state Q3 because we're back to the odd case. When we see the 0, we move back to Q1 because we now have an even number of zeros and an odd number of ones. And finally, the last one brings us back to Q0, which is our one accepting state. Okay, so that's how this is going. And let me get. So what we're going to do is we're going to define a finite automata to be 3 elements: a start state, Q0, then a set of your transition function, which gives the current state a input element and the state that gets transitioned to. So this is our transition function. It's the second argument. It's a list of pairs where the first element is the current state and the input symbol we're seeing. And the second item of the pair is the state to which we move. And then the third argument to our that defines our deterministic finite automata is a list of final states. So we can have more than one final state. In this case, we have only one final state, which is Q0. So we're going to hand a string like this, which defines a finite automata, to our list function that is simulating the finite automata. So here is the simulation of the finite automata. So we are, this again is our input string. And we're going to define, well, let's simulate. We're not going to start with simulate. We're actually going to start with a few access functions. So to make things easier to read, remember our string consists of 3 elements: the start state, which is the car, the transition function, which is the second element of the list, which we can get with the car of the cooter, which is catter. And then the final states is the third argument. We can get that with the car of two cooters. So the first cooter returns elements 2 and 3. The second cooter returns this list that contains only the list of final states, and the car of that would produce this list of Q0. So these three functions, current state, transition function, and final states, allows us to pull apart our list that we're simulating. Then we have a function called inFinal, which is just checking to see whether our current state, which is the first element in our DFA, is in the list of final states. So remember, memQ is like a find function that searches a list, in this case, the final states, to determine whether this element is in it. Okay, so inFinal is just doing a find operation to see whether the current state is in the list of final states. So the big thing we're going to do is a move, where we're going to take our DFA and the next symbol, the next input symbol, and we want to make a move. Okay, so for example, if we are in state, say, so for example, if we are currently in state Q2 and we see a symbol 0, you can see that Q2 0 should move us to state Q2. So that should move us to Q0. So this is what move is doing. It's basically performing one move based on the current symbol. So we have a let where we get the current state, CS. So for example, starting out, let's say it is Q2, let's say the symbol is 0, and let's say that we were currently, that this was, whoops. Okay, so let's say that this was Q2 and the symbol is 0. So we would end up setting CS right here, would get set to Q2, because that is what the current state of the DFA is, Q2. The transition function trans will get set to this list right here. So then what we're going to do is construct a new DFA list, completely new. So basically, we're constructing a new, this was our DFA list to start with, Q2, this transition function, in Q0. We're going to create a completely new list. Now, the only thing that needs to change is the first element of the list. The second element, which is the transition function, and the third element, which is the set of final states, are constant. They don't change. So that's what you see right here, is that the final two elements of the list don't change. Okay, they are the same. The only thing that we're changing is the current state. So this is our current state computation. So if the current state is an error, then we're going to return error. So for example, let's say that we're in some state and the input symbol we see was, let's say we're in Q0 and we see an A. There's no valid transition out of Q0 on A. So we would return error. Okay. So if we've already seen an error, we just keep propagating it. That's what this first if statement right here is saying, is if we've already seen an error, we just keep propagating it to the end. Otherwise, what we're going to do is we are going to try to locate the current state, which is Q2, and our symbol, which is 0. So we're going to create right here this is going to create a list consisting of Q2 and 0, which is our symbol. And it's going to do a lookup. That's what this assoc command does. It does a lookup of this pair in the trans table, and you see right here is a match. So that is going to return Q2, 0, Q0, the complete list. And what we check is to see whether we actually succeeded. If we succeeded, we are going to move to this new state, Q0, which is, this pair is actually a list. Okay, this pair right here, while it looks like a console, is actually a list. So we take the cdr. So catter says take the cdr. The cdr is this part, giving us the list Q0. And then we take the car to get Q0 out. And that's what we return. Otherwise, if it failed because there was no transition, we return error. So if the pair had been list Q2A, it wouldn't have found anything, and now we would have set the error state to error. So basically, the whole point of this move function is to change whatever the current state is to a new state. That's its only goal. The second and third arguments won't change. We just create a new list, copying the second and third arguments and changing the first one. Okay, so that's our move. So then our simulate is taking a DFA and an input. So our DFA string is this string that you see right here. That's our DFA string. And our input is something like 10101, for example, a string. And what we're going to do is create a list of the states that we visited. So basically before, so with 10101, we're going to start with Q0. The 1 is going to take us to Q1. Then the 0 is going to take us to Q3. The second 0 is going to take us back to Q1. And the third one is going to take us it's not right. Okay. So the first one took us from Q0 to Q1. The 0 took us to Q3. The 1 took us, I'm sorry, to Q2. Okay, so the 0 The 1 took us to Q1, the 0 took us to Q3, the 1 took us to Q2, the next 0 is going to take us to Q0, and the final one is going to take us back to Q1. So what we're doing with simulate is we're outputting a list of the states that we visited. So we are consing the, okay, so we're taking the current state of the DFA. So initially the current state is Q0. We're consing that onto the result that we get from the rest of the simulation. Okay, so if the input is null, then we check to see we've exhausted the input list. That's our base case. So if the input is null, we check to see if we're in a final state. If we are, we return a list with accept. Otherwise, we return a list with reject. So we're building the list up from the end. The very last, in this case, the string is going to be reject, because when we're done with the input, we're in state Q1, and that's not a final state. So we're building the string up from the back. Okay, so we don't know that the first thing we actually put on our list is whether we accept or reject. And then we're always consing something onto the front of it. So if the input is not null, that was our base case. If it's not null, we have the recursive case where we do the simulation. So we're going to do a move, and the symbol we pass to move is the car of the input. And what we pass then to simulate is the remainder of the input, because that is what simulate still has to look at. So simulate is always returning a list of states that it has already seen. So when we get back to after we've looked at 1, what we're going to come back with is a list that consists of Q1, Q3, Q2, Q0, Q1, reject. That is what that simulate will return on the remainder of the list. And then we will cons this value Q0 onto the front of it. Okay, so that's, I'm not going to go through the full simulation, but that's essentially what we have going on there, that the simulation is doing one move at a time, and it is adding the current state to the front of whatever list of states it is building up. Okay, and this actually shows you one of the big problems with Lisp, because in this move function, we couldn't just modify the first element of the list. Instead, right here, we created a completely new list. What a waste, because all we really wanted to do was modify this first element of the list. But because Lisp doesn't allow side effects, we have to create a completely new list. Okay, and it's a pretty, even if all we're doing is passing we're not doing a deep copy, so at least we're just passing a pointer to that part of the list and a pointer there. But still, we are creating a list with 3 new elements. And each time we do a move, we create yet another list, which is creating a lot of garbage, because we only use a list for one iteration of move, and then we create a completely new list. So we're generating all these lists and creating a lot of garbage. Okay, so that is one of the problems that we have with functional programming. So we're going to finish by talking about some of the issues that you get with functional programming. Okay, so we'll start with the advantages of functional languages. So first of all, the lack of side effects make them a lot easier to understand, supposedly. Because you only assign a value once, and therefore, supposedly when looking at the program, you know exactly what values each variable has. Whereas in a program with a lot of side effects, especially pointers, you're never sure where those variables might have been modified, like in function calls. So you're never sure that things might not, the ground might not have shifted under your feet with side effects. Okay, I would argue though that, as you saw, in order to simulate side effects, you have to create continuation arguments. And that's not particularly a nice sight either. So I take a little bit of an issue with that, but it's still an argument that advocates of functional languages make. Lack of side effects make programs easier to understand. Then the lack of an explicit evaluation order in your let statements offers the possibility of parallel evaluation. So the fact that lets are innately parallel means if you have a multi-core machine, you can evaluate those expressions in parallel and do the bindings in parallel, thus speeding up the program. Okay, the lack of side effects and the explicit evaluation order simplifies some things for a compiler. So you can use memoization as an example. And that's why it says, provided you don't blow it in other ways. So if you use those set statements, you actually do blow it. But this lack of explicit evaluation order can make parallelization easy. The programs are often surprisingly short. You can write, for example, that Fibonacci, the recursive version of Fibonacci numbers is shorter than the imperative version. Okay. While you may not have appreciated it early in the semester, when you did that pet detective program, that was a lot easier to write it using recursion, and it was much shorter than if you tried to use it without writing recursion. Okay, and the language can be extremely small and yet powerful. What they mean by that is having only a few basic forms. So in Lisp, you have the notion of a list, you have the notion of a cons, a car, and a coulter. You have the notion of a function call. You have the notion of if and cont. And with those, just those forms, you're able to do quite a lot. Okay, they don't have, so you think of an imperative language, it has a whole bunch of other things. It has switch statements, and it has all kinds of operators for doing things. With Lisp, you have one data structure, it's a list. You have a way to append to the front of it with cons. You have a way to pull the first element of the list with car, a way to pull the remainder of the list with coulter. You just have a few simple operations. Okay, but there are problems. And we just saw one of them with performance. It's called the trivial update problem. And in this case, the problem was the in-place mutation. So all we wanted to do was modify the first element of the list. But in fact, we ended up having to recreate the entire list. So that is called in-place mutation right there. And it's an example of what is called the trivial update problem, because it's a trivial update. We just want it to modify the first element of the list with the new state. But instead, we ended up having to create a completely new list. Okay. So that's one of the issues. The initialization of complex structures is another issue. So it can be difficult to put together things that are not lists. So let's say that you wanted to create something incrementally, like a array or a, yeah, so let's say you're doing multi-dimensional arrays and you want to be able to incrementally add to them. So you can basically if you want to add another row to this multi-dimensional structure, you have to recreate the entire thing from scratch again. So you might have you're trying to simulate a matrix. And what you're trying to do is so you have a matrix. You're adding one row at a time. Well, the problem is you add another row, that's a side effect. New row is a side effect. So effectively, you have to reinitialize that structure all over again, starting with the previous 3 rows and the new 4th row. So that is called initialization of complex structures. Okay, and then the final problem, let's go back to, is something called the summarization problem. So let's say you're trying to do a frequency count of words in a file. So that requires that you keep updating as you encounter a new word, you update its frequency count, like in a hash table. Oops, you're not allowed to do that because of the lack of side effects. You can't update those frequency counts. So that's called the summarization problem. You are trying to summarize, kind of accumulate these frequency counts, but you can't because of the lack of side effects. So the only way to do it is to effectively create a completely new hash table or association list with only one element of the association list modified with the added frequency, with one added to that frequency count. So basically, you would use an association list, which is like a hash table, but you have to keep recreating that association list completely from scratch with only one modification each time. So these are 3 things are called the trivial update, instances of the trivial update problem. And it is an issue that gives academic researchers oodles of dollars to play with because they spend lots of time figuring out how to get around this. Because while as a programmer, what you're effectively doing is creating a new list each time, like for that deterministic finite automata. The scheme interpreter is not that stupid. It actually is not trying to create a new list every single time. It's trying to realize that, oh, I can modify an existing list. So to you, there's no side effects. The scheme interpreter is side effect central. It is, without you knowing it, trying to commit side effects. That's the same thing you saw with the tail recursion and reusing the stack frame. Theoretically, it's just a recursive call after recursive call and a whole bunch of stack frames accumulating. But in practice, it's not using an accumulation of stack frames. It's using a single stack frame and a go-to statement. Okay, if you remember that greatest common, if you remember way back, if I can find it. Right here with the greatest common denominator problem, what it was doing was it was, instead of, here is what you write. So you write a perfectly recursive version of greatest common denominator with 2 recursive calls to GCD. Here's how the interpreter translates it. It is not recursive at all. It looks like an imperative program with go-to statements. So that is the functional language interpreter basically using optimizations to improve performance. Okay, so scheme and functional languages in general with all their lists typically make heavy use of pointers. Pointers create locality problems. Arrays, everything is next to each other. So you can pull things in like on a cache line and it's really efficient. But with pointers, things can be all over memory. And so the next element in a list can't be pulled in easily because it's not physically adjacent to the previous item. It's somewhere way off in memory. So you have to keep pulling things out of memory rather than out of cache. So the heavy use of pointers creates locality problems and inhibits the use of cache. Frequent procedure calls is not good because you end up with a lot of overhead with having to push stack frames and pop stack frames. Then associated with that is a heavy space use for recursion because every stack frame adds an additional thing that needs to store registers, return pointers, and the like. And then because you're not having the programmer do it explicitly, you have to do a lot of garbage collection. Like if you really are creating new data structures every time, like in that finite state machine example, if you keep creating a new list with each new move, then the previous list needs to be garbage collected. Okay, and then it is difficult. It requires a different mode of thinking by the programmer. As all of you know, you're taking hours to do problems that you could probably do in a few minutes with Python. Okay, so a completely different way of thinking. Basically, you have to think in terms of recursion rather than in terms of loops. And then it's difficult to integrate I/O into a purely functional model because I/O is inherently side effects. Same thing with graphical user interfaces. You write to the screen. It's a it's a side effect. So you have to somehow integrate IO, which is side effects, into this model. Okay, so again, whether you like functional programming languages or not, pretty much depends on your way of thinking. We just wanted to introduce you to it here in this course. I can tell you that you've seen a lot of it has been, their ideas from functional languages have found their way into scripting languages. Also, some of the more recent frameworks for doing website programming, like I think React is the current most popular framework for doing JavaScript web programming, and it is fairly functionally based. It's more of a functional programming paradigm. So a lot of frameworks basically make use more of declarative programming and function calls. So you may well see it in the real world. Okay, so with that, I'm going to let you all go. If you have questions, feel free to stick around. I can answer them. And again, office hours will be abbreviated today. I'll have to end them at 2:50, but I will try to come online tonight if you're having difficulties. And finally, I will see you one more time a week from Wednesday, May 5th, 3:30 p.m. Okay, so have a good weekend. Good luck with the rest of your finals, and I will see you in a week.
So I think it might be an issue with the way I've declared